other slides we'll try to understand this in more detail. Then there is losses in optical fibers. It is like when we were discussing laser, I told you that whenever we make light incident on any material medium, so the light which we get in the output here, that is attenuated light. There is loss of this intensity of this light. Why there is loss in intensity of light? This happens due to interaction of this light with the material medium. Similar thing happens here, because this is optical fiber. This is of silica material. So there is interaction of light with this material, and there are number of losses. There are a number of reasons. I'm giving you a rough idea. So there is number of reasons for losses in optical fiber. So we have to take that into account, because we have to send information signal, and they should not, that signal should not distort. It should remain intact, or so that information, quality of information and the speed of the information through the optical fiber is there. So when we have sources and sensors for optical fiber, we have applications. We can make sensors using these optical fibers. We can make smoke sensor. We can make temperature sensor to sense temperature. The number of such sensors, we'll see some of them. Then we have applications of optical fiber in communication. We'll see applications in different. So before starting with optical fiber, this new chapter, let us discuss basics, very basic fundamental concepts of physics, so that you can understand, to refresh what you have earlier done. I want to refresh that in your mind, so that whenever we apply those concepts, earlier concepts, you have some idea of those concepts, or you have that in your mind. So let us start with the first basic concept, and the first basic concept is about refractive index of the medium. If we are asked to define refractive index of any medium, we start giving a mathematical formula, that it is speed of light in vacuum to the speed of light in that medium. This ratio of speeds of light in vacuum to the medium gives a refractive index of that medium. Okay, this is not incorrect definition. This is true. This is correct. No doubt about that. But we have to have some better idea about refractive index of the material, or refractive index. What we mean by refractive index. You all know that it is optical property of material, because it is whenever we send light through any material medium, then we talk about refractive index of that medium. So it is optical property of a material, and it measures how strongly the material resists the transmission of light. More is the refractive index of the medium, lesser is the speed of light in that medium. So that means it is sort of resistance to the speed of light. So bigger resistance to the speed of light means bigger refractive index of that medium. Lesser is the refractive index of the medium, means more will be the speed of light in that medium. So roughly I'm saying that this gives you idea. This refractive index, if I know what is refractive index of a medium, then I have little idea about the speed of propagation of light through that medium. Okay, so means it is proportional to, refractive index is proportional to, as I said, that it is, so, or you can say speed of light is proportional to what? It is proportional to, inversely proportional to refractive index. As I said, that more is the refractive index, it offers more resistance to the speed of light, or light slows down more and more in that medium, having more refractive index. So there is inverse relation between speed of light and refractive index and speed of light in that medium. And we can write, if I write proportionality constant as c here, that is speed of light divided by n. So this is how we define refractive index. Refractive index n is now c divided by, I can write it as p. So this is my definition of refractive index. It is a resistance, it offers resistance, or we see it in terms of resistance offered to the speed of light. Okay, you all know that speed of light in free space or in vacuum is 3 into 10 raised to the power 8 meter per second. So if refractive index is known, then what fraction of this c will be the speed of light in the medium, that we can find. Okay, so c divided by nu gives you fraction of light, means speed of light in vacuum. So fraction of that speed. So it is always less than the speed of light in vacuum. So that fraction is always lesser. So v is always lesser. So light travels slower through a medium, as I said, that it is maximum in through vacuum, and the rest is divided by n. In all other media, it will be less than this c, because we will be dividing with this n, which is always greater than 1. So this is definition. I have already written it, that refractive index is velocity of light in vacuum to the velocity of light in the medium whose refractive index we are finding. Let us take 2 examples just to make you give you better understanding, that refractive index of glass is 1.5 and refractive index of water is 4/3 or 4/3. So then now we can predict, I know refractive index of glass is 1.5. So it will reduce when light moves through this medium, light will get reduced by this factor with then the speed of light in vacuum. So we can write it here. If you write refractive index, or v is c divided by 1.5, so that means it is reducing speed of light by 1.5 factor. And similar is true for this when we use this. So you can predict what? You can predict speed in both by making this, putting these values or using this refractive index. So I can predict that speed of light, this is 3 into 10 raised to the power 8 meter per second in vacuum, divided by refractive index of glass gives you speed of light in glass. And this is 3 divided by 1.5, that is 2 into 10 raised to the power 8 meter per second. So speed of light in glass, in glass whose refractive index is 1.5, that gives you fraction of light, or fraction of speed of light in vacuum, and that fraction is 2 into 10 raised to the power 8. Then we have in water speed of light by using this, that is refractive index of water, we can calculate that it is 2.25 into 10 raised to the power 8 meters per second. Okay, so now as I said that whenever there is change in medium, light goes, you can see that speed of light in vacuum is 3 into 10 raised to the power 8 meter per second. It goes to medium 1, or you can say this new medium, then its speed, it gets reduced and it becomes 2 into 10 raised to the power 8 meter per second. And when it goes to this medium having a refractive index of 1.33, so then it from this value it increases a bit, it becomes 2.25 into 10 raised to the power 8. So with change in refractive index, there is change in speed of light through that medium. Now light, when it goes from one medium to the other medium, we see change in speed is there, and with that we also see another phenomena, that is bending of light. So here light is made incident. You can see that I have this medium this is having refractive index N2. This is refractive index of this medium, and this is medium having refractive index N1. And light is made incident on the interface of these two media at this point, and then we see that there is bending of light. So this phenomena, you all know, this is called a refraction of light, and this is due to what? This is due to change in refractive index from N1 to N2, due to change in speed of light from this value to this value. That depends on what is the refractive index of this medium and what is the refractive index of the other medium. So we are interested in finding these angles. This is angle of incidence. This phenomena is what? This is angle. This is reflection, that light bends in the same medium. This is theta r, and this is phi 2, which is angle of refraction, angle made by this ray which bends and goes to the other medium, that makes with the normal. This angle is angle of refraction. Similarly, here light is traveling earlier through this N1, and then it goes to N2. And here it is in this medium, you can say denser medium, and then it goes to, it is bending towards the normal. Here you can see that this should have been the straight line path of this light ray, but it bends towards the normal. Here you can see that light bends away from the normal. This is the actual part, straight line path, which it should have followed if koi change na hota medium ka, but as there is change in medium, so it bends, and it bends away from the normal. So that's why I'm saying that this is what? This is a rarer medium and this is denser medium. Similarly, here I'm saying that this is rarer medium and this is optically denser medium. And what about the relation between these angles? Because there is bending of light. So by what amount it is bending, that is measured by angle made by the ray with the normal. Okay, so in this case, we have what? We have first law of reflection of light. So first law of reflection tells you that angle of incidence is always equal to angle of reflection. So always we write that theta 1 is equal to this, or angle of incidence is equal to angle of reflection. And relation between angle of incidence and angle of refraction is also important. And this depends on what? This depends on N1 and N2. So this is given by Snell's law. We say that N1 sine theta 1 is equals to N2 sine theta 2. For this given medium, for fixed, we say that N1 and N2 are fixed. Okay, we can make light incident at different angles of incidence here. And we see that different angle of refraction here. So as these two are fixed, so ये दोनों equal कब होंगे? If I increase theta 1, so this sine theta 2 should also increase, या theta 2 should also increase. Okay, so let me give you, this is Snell's law, N1 sine theta 1 is equal to N2 sine theta 2, and this is what? This is angle of incidence is equal to angle of reflection. And you can see here that N2 is greater than N1, then phi 2 is less than phi 1, because we go from a rarer to denser medium. So in denser medium, angle made by the ray with the normal is lesser. It bends towards the normal, and other way around, when it goes to the rarer medium, it bends away from the normal. Okay, then we have, this is showing what? This is showing glass interface here, and this is air-water interface. In case of air-glass interface, it is interface between these medium's N1 is N1 and N2 refractive index is 1.5, whereas refractive index of the denser medium in this case is 1.33. So if we make this is again N1 sine theta 1 is equal to N2 sine theta 2. So you can see that we are not changing N1 is N1, and theta 2 we are changing. So you can see here that it is 45 degree, and this is N1, this is N1. So this product is, this is what N1 sine theta 1 we have fixed. So now it depends on what we have. If we change it from to lower value, then what should happen with it? This should increase. So that's what you can see here. So whenever light goes to glass, it makes, and according to Snell's law, you can find what should be the angle, this angle here. It is 28 degree according to Snell's law. And again, if I make light incident, but now it is optically, comparative to this, it is optically rarer medium. So bending is slightly less. This was 28 and this is 32. This bending is less because of this refractive index is lesser than the refractive index N2. Okay, you all have done this, and there is another thing, that is this is reversible. Means when we make light incident from rarer side on the interface and it goes to the denser medium like this, then if I make it incident at 45 degree and it bends in the denser medium towards the normal and it makes 32 degree angle with the normal, then if I reverse the path of this light, and if it is 32 here, then it makes 45 here. That means N1 sine theta 1 is equals to N2 sine theta 2. We are not changing, we are keeping this and this same. So N1 and N2 we are not changing. So we are fixing, or we have this. First we have this. That means we say that we have 45 degree, and we find what this is. Okay, and then I fix this. Means what? This should be equal to this sine. They should remain what when we fix these two. So this, to make this equal, we have to see this. So refraction of light, you all know refraction of light. There is bending of light when there is change in medium. It goes from medium 1 to medium 2, from optically rarer medium to optically denser medium. So this phenomena you see, you have observed this phenomena whenever you see around you, you see swimming pool, base of the swimming pool, it looks bit raised than the actual depth of the pool. Shallower आपको appear होता है, या we dip the pencil in glass full of water, you can see that this phenomena of refraction, when you see that it appears, pencil appears, that there is bend in the pencil. So all you can see, or you can say that fish, it appears that it is closer to the surface than the actual depth. And this is what is seen by a fish. Again, there is bending of light, there is phenomena of bending of light. Or you can, if you see through a thick glass slab, you'll see objects, they appear displaced from their original locations. So that is what is there. And we have most important thing, which is principle of optical fiber, communication through optical fiber, or propagation of signal through optical fiber. That is total internal reflection. How light travels through optical fiber? It is through multiple total internal reflections. As I have drawn it earlier also, this is my optical fiber, and light is sent through this optical fiber. When light goes into this optical fiber, due to change in refractive index, because refractive index of this is air, we are sending it from air and it is going to some medium having refractive index N. So there will be bending of light. It bends towards this. There is another interface here, and then total internal reflection happens at this interface, and multiple total internal reflections are responsible for propagation of light through the optical fiber. So basic thing due to which it remains, it does not leak out of the optical fiber. It does not come out of the optical fiber. Light remains within the optical fiber, or it is confined to the optical fiber. That is due to this total internal reflection condition. So we'll see this in more detail, what this total internal reflection is. You see here, you have done this earlier. This is my denser medium, and this is some optically rarer medium. Our light is made incident on the interface from the denser side at angle 0. This is angle of incidence is 0 here, and it passes undeflected like this. Again, it is from Snell's law. You can see that n1 sine theta 1 is equals to n2 sine theta 2. Okay, so these are fixed, theta 1 and theta 2. And then we see that sine of theta I is, this is angle of incidence. If this is 0, then this makes this side 0. And as this is already fixed, so this should also be 0. So that means theta 2 is also 0. So it goes undeflected. And if light is made incident on the interface at some angle phi 1, then we see that partially it is refracted and partially it is reflected. And then if we go on increasing, you see it according to Snell's law, if we go on increasing this also increases. Angle of refraction also increases as it is going to the rarer medium. And the angle at which, angle of incidence, at which angle of this refraction becomes 90, that is called critical angle. And that expression I have written here, because you see that this is n1 sine of angle of incidence theta I or theta 1 is equal to n2 sine of angle of refraction, you can say theta r. So at this point, n1 sine of theta c, this is called critical angle, and when this angle is theta c, angle of incidence, this is 90, so sine of 90 is what it is, 1, or we can write that sine theta c is equals to n2 divided by n1, or then theta c critical angle is sine inverse n2 over n1. So that means for different combination of mediums, you have to find this, and it depends on what it depends on ratio of their refractive indices. So it is different, critical angle is different, at what angle total internal reflection will start. And after this, when we make angle of incidence greater than this critical angle, then you can see this total internal reflection phenomenon. So what should be the angle for glass air interface for total internal reflection to happen, for some other combination water air interface, that we can find that critical angle, at what angle light should be made incident to see total internal reflection. That is decided on the basis of n2 divided by n1. So sine inverse of n2 over n1, that gives you that angle of incidence. So total internal reflection, to see this phenomena of total internal reflection, there are two conditions. One is that light should be made incident on the interface from the denser side. You see here n2 is denser, sorry, n1 is denser, n1 is greater than n2. And angle made by the light which is made incident should be greater than the critical angle for that system or for that combination or for that interface. So, and that angle should be greater than critical angle. And what is that critical angle? What is it is 28, 30, 40, that depends on sine inverse n2. So you can find it as we have done. You know what is refractive index of this is glass, refractive index of water is 4/3. So if we have water glass interface, so this ratio and sine inverse of this, then you can see that what is the that required condition. So it should be 4/3 because it is 1.33 divided by this sine inverse of this. This will give you what it will give you. Critical angle, or for total internal reflection to happen, what angle should be there of the incident light with the normal. So these are the basic concepts which you have already done, and you are master of these concepts, and we'll be using these concepts. Some more concepts I'll quickly go through during next lecture, because this is already 11, and then we'll start with optical fiber. Okay, if you have anything, any queries till